Welcome to the dynamic learning hub of XLR at Andheri East. A prime spot conveniently located at just a 5-minute walk from LIC Andheri Metro. In our journey of over a decade, we have proudly trained over 2 lakh students. We have also been recognized by Deloitte, Silicon India, and other accreditation bodies. Experience learning like never before in our spacious and comfortable classrooms. With high-definition projectors and state-of-the-art acoustics in place, we ensure effective learning even to the farthest point in the room. The hybrid mode is a game changer as you can enjoy the benefits of a light classroom from the comfort of your home. Even if you happen to miss any classroom session, you can still attend the same session with the same trainer at the same time at your convenience, maintaining consistency in your learning progress. Wanna get started? Join us for a demo or career chat over a cup of coffee at our Andheri branch. XLR. We don't just train, we build careers.
Yes, so the collaboration with XLR was an excellent one. We conducted a Power BI workshop with Advanced Excel over a span of 3 days. The workshop was almost 12 hours long in total. Mr. Karthik, who was an amazing trainer, helped the students understand the concepts deeply. I am sure that the students will be able to apply these concepts in their careers as well as their daily lives.
The trainer, Mr. Karthik, was an excellent person where he explained in very detailed manner on how to give great insights using very complex data sets.
So it was a machine learning workshop. We learned a lot from the course and it was a great experience attending the workshop.
The trainer was very helpful. He had a hands-on approach with his teaching and it was fabulous.
This was a great experience for me. So I would absolutely love it if XLR and its team would come again to our campus and conduct more events like this.
It was a great course and it started from basics and took me to a great extent.
The experience of the workshop was really nice. The feedback from all the students was positive. They understood the concept. The workshop was also practical based with some questions. The experience with XLR was very smooth. They helped us in conducting the workshop smoothly right from the booking of the vendor and deciding the course till the distribution of certificates. In overall, this workshop was a success during our Technical Fest Atmos, and I thank XLR for being a part of it.
I was very much interested in learning digital marketing course for a very long period of time, but I don't get a proper platform. So later for my college, I get to know about XLR and I enrolled in XLR course. It was really good.
Good evening, all. I hope you are doing well. Good evening, Sunil. So,
Yeah, hi. Good evening. Good evening, everyone. Sorry for the late. I had something I had to attend, so it was late. And so let's start with our session today. Today we'll be discussing about decision trees, which I mentioned yesterday, and how support vector machines work. And then we'll be working on a time series forecasting problem. Then once time series forecasting problem is done, we will be working with clustering algorithms to understand how clustering works. In case of forecasting, what we will be doing is we will be using only we'll be using AR and moving average and ARIMA. Today we're going to do Sarimax because in spite of using GPU, I couldn't train the model in Colab. And even for XGBoost also, the RAM is crashing, so I couldn't do that one as well. So we'll be doing Arima and then Facebook Prophet, which is widely used currently. I mean, it's kind of advanced one Prophet model. So we'll be using that one. Apart from that, there are deep learning network which can be used to train to do forecasting, particularly LSTM networks. But in this class, we'll be sticking up to Prophet. And for clustering, I will give you basic idea about how clustering works, and then we'll work on a single problem. So coming to what we discussed, let's start with decision trees. Let me share my screen. So coming to decision tree algorithm, what happens in case of decision tree is nothing but an hierarchical structure. If you look at a tree will have single root and it will branch out when it as it goes upward, and then it will have different branches, and each branches will have smaller branches, and further it is divided, and the final smallest structure will be the leaf. So similar way what we do in decision trees is like, but the difference between decision trees and trees is that it is an inverted tree actually, because the root node starts from the top and then it branches out as it goes towards the bottom. So what happens is like at every node it tries to take a feature and then try to split the data set based upon an intelligent guess, or based upon a particular hierarchy within that feature, and dividing the data set into two sets, and will check in the resultant nodes. What it does is like it will try to check if the nodes are pure, or yeah, what is the information gain that is getting by making the division. And if the nodes are not pure, or if the information gain is too high, then what happens is like it will further split the node, and then it keep on continuing like that until all the leaf nodes in the bottom. Here you can see this bottom node, until all the bottom nodes are having only single type of elements and doesn't have any other elements, then it is considered as pure. And this division continues until that level, and once it reaches that level it will complete training. But if we allow the model to go up to the maximum depth, what happens is like the possibility of overfitting will increase. That's why what we do is like, instead of allowing it to reach the maximum purity, we try to restrict it by pruning the tree, or by allowing the maximum depth, or number of maximum depth, so that what happens is like it will only can go up to certain level, or we can even try to restrict the further training by using by keep creating a restriction like minimum number of leaves, or minimum number of samples in every split. So we try to use these hyperparameters in order to control the structure so that it will not the model will not get over fitted. So this is how a decision tree looks like if you look at this image. So there are two types of decision trees. One is ID3 and one is cart algorithm. So in case of ID3, what happens is like every node is measured on a concept called entropy or purity of the particular node over there. And when it comes to cart algorithm, we try to focus upon Gini impurity. Like we try to predict what are the categories that are, I mean, what are the samples that are available within that particular n node. So based upon what kind of concept you are using for that particular node, these decision trees are divided into either ID3 or cart algorithms, and there are different. Let me increase the size of. Okay, I will increase and I will share this. So these are the terminologies related to decision trees. So the root node is nothing but the top node which you observe here. So this is called as root node, and that is the initial node at the beginning of decision tree, where entire data set starts dividing based on various features or conditions. So these features can be selected by decision tree randomly, or it tries to understand by making this division. Like for example, let's take you have three features like feature 1, feature 2, and feature 3. Initially, the decision tree try to use feature 1 as a division parameter. Then what happens is like it tries to see if I use this particular feature to make the division, what is the information I'm gaining, or what is the entropy that is happening in the next leaf node. Based on that, it will select the feature that initially has to be used as the initial division of the data set. So that's how it starts using the features that are used to split that entire data set. And decision nodes are the nodes that result from this root node. If you can see, these nodes where there are further branches. These are considered as decision nodes where further decisions are made or intermediate decisions are made based upon rest of the features are based upon rest of the conditions within the tree. And leaf nodes are nodes where there won't be any further splitting. If you see at this structure, you can see this leaf node in the nodes here, which are not having any division here. So these are considered as leaf nodes, or even the bottommost nodes are considered as leaf nodes. And subtree is like structure subsection of graph. Like for example, if you take this one, this can be considered as an subtree, or this part can be considered as a subtree, or this part can be considered as a subtree. So these are considered as subtrees. And pruning is process of removing or cutting down specific nodes to prevent it from overfitting. Let's say our decision tree is having 1, 2, 3, 4 hierarchical structures here, and this is this is the maximum depth it can go up to. But when we look, in order to avoid overfitting, what we do is like instead of allowing it to reach this level, we will prune this branch so that what happens is like there will be only three hierarchical structures. That means 1, 2, and 3. And even though there is some impurity within these leaf nodes, still it will not make any further decision because we don't want the model to proceed further, and we want to restrict the building of trees up to only three levels. So by doing pruning, what we are doing is we are limiting the depth of the tree so that the model will not get overfitted. So that's what the pruning means here. And branches are subtree, which I already explained. And parent and child nodes are the parent. Any node where the decision is made is considered as parent node. Any node that is deriving from the parent node is considered as child node of that particular parent node. So these are the terminologies you need to understand. And some other terminologies are what is the maximum depth. Like depth indicates like levels 1, 2, 3, 4, and these levels are maximum depth. And minimum samples in every split. That means after splitting, every leaf node should be having some samples within that one. Like for example, if I consider minimum number of samples after split as around 10 samples, if this day if the if the data set is being divided at this node, and after division, if any one of these leaf nodes contain less than 10 samples, then this division will not be considered, and it will stop division at here itself, because we kept an restriction called as a minimum number of samples that should be there in the leaf node. So there are other hyperparameters as well we need to understand in order to work with this decision trees. And by using decision trees, we can construct a random forest algorithm by using bagging techniques. I already explained you this one yesterday, where we create multiple decision trees, and then a subset of data or subset of features information is passed to each of this decision tree, and each model, each decision tree predicts value independently, and then that predictions majority voting is considered in order to derive to the final prediction. In case of classification, when it comes to regression, we consider the mean value or average value of all the predictions that will happen in each decision tree. So that's how this bagging works in terms of random forest. But when it comes to boosting, what happens is like they will entire data is passed through, or a subset of data is passed through initial model, and after completing the model, then the next model is built, and then some data is passed through the next model. Through this, what we are doing is we are boosting the predictions. Like we are using the predictions that happen in the first level in the next model, and from this model in the next model, like that, and we are boosting the model, and these are boosting models work. And some of the examples related to boosting technique is XGBoost. So this is one of widely used algorithm in machine learning in relation to boosting. So yeah, to explain how this works, to understand how this decision tree works, if you look at this one, there will be root node, and here it will decide upon a particular feature, and then splits the data set into next level, where the decision nodes again keep on splitting the information, and finally it will terminate into terminal nodes. If you take this particular data set to understand what happens at every level, you can look at this scale. You can look at this here. So if you look at this, we consider temporary weather has initial level of initial level of splitting, and based upon weather, we have three types of options in case of weather. So one is sunny, cloudy, and rainy. So it will split the information based upon sunny and cloudy and rainy. It's nothing but we are segregating all the data points based upon based upon the group by, or we can simply consider like we are grouping the entire data set based upon this weather column and based upon the values that are present in this weather column. Like for example, it will take this sunny, and if then the next level of splitting will happen based upon the next feature, humidity. And at humidity, we have two options. One is high or normal. This is like whether a game, this data is related to whether the game happens or not. Based upon that information, if you look at this one, if the weather is sunny and there is high humidity, then there won't be any game. And if the weather is sunny and the humidity is normal, then there will be game. And if you look at this one, this is considered as final leaf node, because after this split, all the values or all the data set is having only this particular category. That means as we are considering this to be pure node, none of the data points or none of the rows will contain yes as answer when we split the data like this. And in this case, none of the data points and none of the rows contains the value as yes when when we do the split like this here. And when you look at this case, whenever the weather is cloudy, by default the game is happening. That's why there are no further split, because this entire whenever there is the weather is cloudy, despite of what the humidity is, still the game is happening. That's why this pure node, and there is no further division here. And the same thing happens in case of wind. So if there is some impurity here, what happens is like there will be further step. Like for example, we have temperature as well. Then we use temperature to split the data and to see and check whether there is any impurity. Impurity means, like for example, our class is yes or no. So what we're trying to predict is if the game happens or not, yes or no. So any node will be considered as pure if all the rows that are resultant of the split that happened considered only one type of values, like either yes or no. So then it is considered as pure. And if there is mix of this one, then it is considered as impure. And if the number of the data separation is like 50% of yes and 50% of no, that is considered as highly impure. because it's like we are not coming up to any decision based upon that particular split. So any questions so far? Anyone, any questions? So now coming to support vector machine, this is one of widely used algorithm. Generally, this is used for classification, but still for regression also this algorithm will be used. So this particular support vector algorithm works by dividing the data or by finding a hyperplane which separates data into two categories. So this concept of decision planes or decision boundaries are selected based upon support vectors called support vectors. These support vectors are nothing but like for example, let's say we have some data and we are trying to we are trying to segregate these data into two classes. So what we do is like we create an higher dimension. I mean, initially we try to separate the data in a two-dimensional plane. If we are unable to do that one, then we go to three-dimensional. And what the support vector machine does is like it creates some higher level dimension data where the data can be separated by a plane. Because when we speak about higher dimension data, then we have to talk about only plane, and we try to create an imaginary plane which can separate these two classes effectively. And when we say these two classes effectively, that means the distance between the closest data points to the hyperplane in both the classes should be maximum. So that's what we are trying to identify. Let me share an image. Let me see if I have an image here. No, I have image. Just give me a second. I will show you an image. Yeah, let me share my screen again. So if you look at this case here, our main goal is to come with this decision boundary. If you can see this dotted line here, our main goal is to find out this decision boundary, which will be placed in such a way that if you look at these are support vectors. I mean, if you see these two blue dots here and one blue dot, red dot here, these are considered as support vectors because these are the closest data points belonging to these two classes. I mean, if you see all the data points, rest of the data points in blue class are beyond this line, and all the data points in red class are beyond this line. And ideally, what we're trying to find out is we are trying to find out the support vectors which are close to the plane. And our main goal is to maximize the distance between these two support vectors from the plane. That means when we maximize the distance, what happens is like we will be able to effectively separate these two classes. If this distance is very less, what happens is like there is a possibility that unseen data might fall among this level, and then the separation will not be that effective. So that's why our main goal is to increase this margin or find out a plane which has the maximum gap, maximum distance from each of the support vector. So this is in two dimension. If you look at in three dimension, you will understand this. So initially, your input space will be like this. In two dimension, you can see like you will not be able to separate this by an hyperplane. But when you project this data into next dimension, you can create a plane which will be able to separate these two classes. So ideally, even in case of principal component analysis, also what happens is like when we might not be able to separate any of these categories in 2 dimension. But when we project them into higher dimension, like third dimension, fourth dimension, fifth dimension, sixth dimension, like that, what happens is like we will be able to identify a separation or a boundary line that can effectively separate both these classes. So that's where that's where we will be able to come with the boundary plane, which can be used to segregate two different classes. So that's how this support vector machine works. So any questions, anyone? So generally, support vector machines in most of the cases work effectively. There was a question. Okay. So support vector machines work effectively when you are unable to separate the two categories, because we are projecting this data into into higher dimension. That's why it works effectively when we are unable to separate two categories or two classes in general. And in some of the cases, even though this is not an ensemble model, this model works effectively in for most of the business problems. So we can use this one. And if you still have any question related to that one, imagine this like an fence. We are trying to separate between let's take cats and rats, where our main goal is to maximize the distance between the closest cat to the fence and the closest rat to the fence, because we don't want this cat to catch the rat or any other animal like that. So try to understand this way, and our main goal is to find out the best hyperplane, which will have the maximum distance from the closest data points in each class. So that's how this support vector machines work. Anyone, any questions? So now let's go with our time series problem. Um, Let me share my this. As of now, don't consider the results here, because I didn't focus on results. But our main goal was to show you how this algorithm works. So generally, right now, there are multiple ways to forecast the data. And time series data is nothing but data that is having um, what is it? The data that is time dependent. And so every data point, I mean, every entire data is majorly dependent or majorly influenced by the time component, and majorly dependent upon by time component. And this is kind of sequential data. And what happens is like this kind of data is unique because the data is not only about the values, but also the order in which they occur. Like, I mean, in general, what we do is like we randomly take the data and do like, even if you remember in yesterday classification or regression projects, what we did is we randomly split the data to train and test. But in case of time series data, we cannot do that one, because the data is time dependent and it should be in order. If it's not in order, then we will not be able to we will not be able to forecast the information. That's why this time series data is unique in its own way. And there are few features that are related to time series data. One is temporal component. Temporal component is nothing but it's like every observation will be having a timestamp. Like, for example, if you see monthly sales figures, or daily weather data, or hourly weather data, or stock prices, or commodity prices, so you can see that there will be a timestamp that is associated with each observation, and this time creates a natural order within the data. And other feature of time series data is sequential nature. That means, unlike other data sets, where we don't focus more upon order, time series data must be analyzed in the sequence in which it was recorded. Like for example, if you take ECG or EEG or any IoT sensor data or stock prices or even this sales data, we need to have it in a sequence, because in order to understand what is happening today, we need it will have some relation with what happened yesterday or what happened before this particular timestamp. So that's why the sequential nature is more important in case of time series data, and there will be different patterns and trends that are associated with for time series data. One of the pattern is trend. That means the trend can be like I mean, you can see either an increase in trend or decrease in trend, or they can sometimes there won't be any trend within that data. For example, let's take climate change, where we can observe like an if we observe if you take an average the temperature data from 1900s to current date, you can observe an average global temperature is increasing. Even we also face the same. I mean, we also experience the same thing on day-to-day basis, where earlier we used to have an average temperatures below 40. Now the average temperatures are going beyond 40 degrees. It's like a continuous increasing trend. Similarly, you can take inflation, or you can take a value of any good, or you can take any value of any food product or something. In general, I mean, there will be fluctuations on day-to-day basis or seasonal basis, but in general, you can see an continuous increasing trend, because as the inflation increases, automatically the price of the particular good will increase, because we need to consider that inflation as well within the price of that particular commodity. So that is considered as trend. And another pattern that we can observe in time series data is seasonality. Like you might have, for example, seasonality is nothing but regular patterns repeating over a specific period of time. Like for example, if you take AC sales or refrigerator sales, you can see an increase in sales during summer season and a drop in sales in every winter season. This can be observed in most of the years. Similarly, the cases with ice creams or sweaters or what else you can say, like I mean, even these commodities like rice or vegetables like tomatoes, where when during the harvest season we can see a sharp drop in prices, and as the harvest season completes, we can see an increase in prices. So there will be seasonality associated with most of our for time series data. And other thing is cycles. So these cycles are nothing but fluctuations over time. Like I mean, these I mean, even though this is considered looks kind of seasonality, but actually seasonality is different from cyclical data, in such a way that cyclicality is related to economic or business cycles. Like for example, let's take iron ore business, or some other business which is cyclical in nature. I can't recall right now. So if you observe iron ore business is generally considered as cyclical in nature, because prices or demand for this iron ore will increase during a part of time, and it will get reduced during another part of time. For example, even if you take cement also, what happens is like during the rainy season, there won't be many of the construction will be happening. So automatically there will be a reduction in demand for cement, and rest of the period you can see an increase in demand. So this cyclicality will also have a major impact in time series data. And there is another pattern that we can observe in time series data, which is nothing but noise, which we cannot avoid. And noise is like sharp fluctuations in data, which we observe, and we try to avoid that particular noise in that one. And some of the examples of time series data is like weather data, website traffic, energy consumption, medical data, and stock market prices, commodity prices, even your heart rate measurements, or ECGs, EEGs, all, even IoT sensor data, all these are considered as time series data. And there is another concept called stationarity. We need to consider that stationarity is nothing but we need to consider that the time series model doesn't change over time. I mean, the statistical properties like mean or variance will not change over time. So that I mean, if this holds true, then it will be easy for us to forecast. Make the forecasting of our time series data. So this time, when you work on time series data, your most of the work will be in creating either data or working toward performing analysis through graphs and plots. So most of your time will be spent upon this particular data analysis only. And forecasting, you can to in order to do the forecasting, there are multiple models. Initially, they used auto-regressive models, which uses linear prediction, which considers linear relation between previous data point and the current data point. And then later they used the moving average, where we calculate the average by moving it for every step, and then they build its moving average model. And Arima is, and then later one advanced model was Arima model, which is nothing but combination of auto-regressive and moving average, AR and moving average, and with an component called integration. So Arima full form is auto-regressive integrated moving average model, which generally provides better results. And the another one is Sarimax, which is nothing but Arima, which takes into account seasonality as well. So that's why that's considered as Sarima, Sarima. And so the and apart from that, the other model which is more prominent in forecasting is Profit. Sorry for that. And Prophet is in most of the cases was working effectively. And then as the data in time series is seasonal in nature, by default LSTMs work more effectively, because LSTM works better in seasonal data. If you remember, if you understand, if you look at natural language processing problems, most of these NLP problems are the data is like what do you call that term? Time dependent. I mean, like for example, if you are saying I'm going to watch a, then if you want to predict the next word, then generally if you say watch a, then it might be either be TV or movie. So the word here depends upon what are the words, are the way the sequence of words that are appearing before these words. So that's why LSTM model works effectively in case of NLP as well. And similarly, as an LSTM deals with the sequential data, it works effectively for forecasting solutions as well. So LSTM is also another algorithm which is widely used in forecasting solutions. Yeah. So let's start with this particular project. Here we are taking some energy consumption data. So before going to that one, you can look at this trend pattern. If you look at this particular in, first image, to the left, this, like you can see the time series data here. You can see no trend. I mean, the data is like completely flat, and you don't find any trend in the data. In that kind of data, we will not be able to make any predictions, because we don't find any trend within that one. And the second data is like curvilinear trend, and here there is no linear relation between previous data and current data. So that's why we need to go with quadratic or exponential information in order to make forecasting. And this is like increasing linear trend. And the third one is increasing linear trend, where we can see linear relationship between previous data point and current data point. And there will be linear decreasing trend as well. You can see decreasing linear trend as well, where the data will I mean the values will decrease with increasing time. So there you can see even the both the time data points are interrelated linearly, but the value decreases with change in time. And you can see that seasonal pattern here. You can see that at a certain point of time, at repeated intervals, you can see there is the data is increasing and then further dropping. The data is further increasing and further dropping. This is seasonal pattern, and when this seasonal pattern is combined with the trend, you can observe this kind of pattern. In general, most of the time series data, like sales, in general, it is supposed to be like this, either in increasing trend or decreasing trend. Because but you can see, if you look at the sales data, generally the sales will keep on increasing with time. and there will be seasonality associated with that one. But still, you can observe when you take an average value, or when you take have a look at the data, you can observe an increasing trend or decreasing trend within the data. So this is how seasonal pattern plus linear increasing linear trend looks like. You can also imagine how it looks like when the seasonal pattern plus linear decrease. Like, I mean, instead of growth, you can observe an linear decrease as well, where the plot will be inverted and it will be downwards. Any questions so far? Okay, so I will take that as a no. And Prophet, we need to. This is Prophet is an algorithm which is built by Facebook. Meta right now the company name is Meta. So they build it and they open source this Prophet model, and it's being widely used in industry. So initially, I'm installing that one. Initially, I only wanted to show you Prophet, but I thought like if you know what happened with other previous models also, you'll understand it effectively. That's why I included AR and Arima as well within this one. I tried Serimax, but it's crashing. So here we are loading all these libraries which are required, and then we are creating this function in order to calculate our metric, which is mean absolute percentage error. What we are doing is like we are taking y value, that means current target variable value, and the predicted value, and then we are calculating absolute value and dividing with the original true value, and then taking the percentage of that one, so that we understand what is the percentage of deviation between the true target variable and the predicted target variable. So the data which we will be using is an energy consumption data that is measured every hour. This is from PJM, and I took this from Kaggle, and this data has information from 2002 to 2018 for East region in USA. So the data, it looks like this one. In most of the time series data, there will be some other features as well that are associated with the data pattern. But in general, we will be using only the target variable and the date values in order to do the forecasting. But while performing univariate and bivariate analysis, we will be using all the different data. Like, for example, it's not like energy consumption will be dependent only on time. It will be dependent upon the localities. It will be dependent upon area. Because, like, for example, if we are measuring this energy consumption, the energy consumption can be very high in industrial area, whereas the energy consumption at a specific time in residential time will be comparatively low. Like, for example, let's take an IT hub where the energy consumption will be at its peak during morning 9 to 5, because that's when most of the office will be working. And during the same period, where the residential areas where these IT people live will have lowest energy consumption, because most of them will be in offices, and the utensils are machines that operate during the time period will be comparatively low. So what happens is like when at the night, you can observe this in IT hubs, the consumption will go low, whereas in the residential areas the consumption will increase. So this is how it will be dependent upon areas as well. But when it comes to industrial areas where manufacturing happens, it will be continuously high. So depending upon areas and depending upon locality, depending upon regions also, the consumption will change. So initially, this entire forecasting will include a lot of data analysis. So as of now, we are looking only at date and the consumption values here. But in general, there will be other features as well, where we will be performing different analysis on top of to understand the consumption patterns, and say create clusters of highest consumption, and I mean, whatever the forecasting is, whatever, like, for example, if you take sales data of a store, let's say you have some company, let's say Campa Cola, let's take they wanted to understand where they are having highest sales, in which store they are having highest stores. What they can do is, like, instead of going through just now, instead of forecasting this solution for all the combination of all the source, which is not an effective way to do. Instead, what they can do is like they can try to divide the data across the stores, and they can do the forecasting for each individual store. So what they can do is like they can create multiple forecasting algorithms for each individual store, and then try to see which store is performing effectively and what is the like, for example, in some stores we can see an increasing trend of sales, and in some stores we can see and decreasing trend of sales, so that they can understand like where to focus more, and what they can do to what are the characteristics of the properties that is deciding the trend that is observed in that particular the particular sales. So this is how you need to understand this is the way you need to work up on a forecasting solution. I mean, I'm explaining more here because forecasting is kind of more into data analysis rather than into just building the model. Because if you can build a forecasting model and it can give the predictions, but that doesn't help in making any business decisions. When you are building a model, you need to give some information that will help the business to make some decisions. So that's how we add value to the decisions. We add value to the business. So that's one thing you need to remember always. And so that's why we need to focus more upon data analysis here. So now we can see here we have date value, and we have consumption value here in megawatts. And one more thing is I am intentionally converting the date value into an index value, because it will be easy for me to create plots by using this index value rather than using something else as index and using this x value or something. Because when it is indexed, it will be easy to create some operations like LOCs or ILOCs to split the data, to use data for certain range, or to perform operations on data within certain range. So that's why we use this date time as index rather than general indexes within the data. So this is how the data looks like here. And to look at how the data is operating, you can look at this is how the data is. I mean, the data is being looked at. This is the consumption patterns within the data. You can see like we don't find any major trend here. So that's why the forecasting might not be that effective in this case, because we don't find any increasing or decreasing trend within this data. But we can find seasonality within this data. You can see a lot of seasonality is available, because you can see at every start of every year you can see an increasing trend for every pattern over there, because maybe at that time the consumption is very high over there. And what we are doing here is we are creating features from the data, because that ideally what data we have is we have date time and consumption pattern. So what we are trying to do is we are creating features from this data. So what we are doing is we are creating date, we are creating hour, we are creating day of the week like Sunday, Monday, Tuesday, Wednesday, Thursday, because the consumption will be dependent upon what day we are measuring the value. And at the same time, we are trying to understand whether it's a weekday or weekend, and we are trying to see what is the quarter of the year, what is the month of the year, what is the year, and what is the day, what is the day of the month, what is the week of the year. And we are creating all these features so that we can try to do our analysis. I mean, these features are not used for forecasting, but these features are used in order to perform further analysis on this forecasting data. That's why we are creating these features. So when we do this one, we'll be yeah, we are creating features here, and in this step, there was some duplicate values. So duplicate timestamps, I removed, dropped this one. So I had to add this one. That's why I just dropped these particular duplicates, and we are splitting the data for based upon the from 2015, so that we can use any data. Say, for example, let's say here we have this entire data, but I want to make how can I split the data for my training and testing purpose. So for training, I need to have some data, and for testing, I need to have some data. In case, if you remember yesterday's classification algorithm or regression algorithm, what I was doing is I was randomly splitting the data into training and testing data. But here I can't do that one, because this data is time dependent and it has to be in the similar order. That's why I can't split the data randomly, but I need to split the data on some time frame. So what I do is like taking data up to 2015 as training data, and I'm using 2000 data from 2015 to 2018 as testing data, so that I can cross compare and see how my forecasting model is working effectively. So that's what we are doing here, and we are splitting the data based upon this particular date and creating the train data and test data, and then visualizing the data. See, you can see this is our training data, and this is our testing data. So till this point, we are using this data as training data, and this as to test our model, our forecasting solution. So this to this for creating the forecasted data. Once we forecast, I'm creating this function to forecast the predicted trends by the model. And yeah, as I already mentioned you, I'm using AR and Arima in order to show you how initially these particular models work. So if you look at this particular step here, we are trying to fit an ARIMA AR model. AR is nothing but autoregressive. And in case of autoregressive, what we are trying to do is that in autoregressive model, it predicts that assumes that the current value of time series is based upon its own previous values, and we can decide that, like for example, tomorrow sales. It assumes that tomorrow sales are dependent upon today's sales, and based upon this one it tries to add some value. Like for example, if I say let's take lag of around 2 years, then what happens is like it will observe the quantum of increase within last 2 years for every day, and use that value as measurement, and then increases today's value from yesterday's value by that amount. So that's how this auto regression works, and it assumes an linear regression. But if you remember, most of the forecasting and most of the time series data is not linearly correlated. So that's where this auto-regressive model will not work effectively. Here you will see a term called lag. Lag is nothing but how much beyond it has to go. Here I'm using 24, which means as the data is early data, I'm asking it to take data points from for last 24 hours. So while making the decision, it uses last 24 hours data and then tries to predict current data point based upon last 24 data points or 24 hours data points. That's how this auto-regressive model works. Ideally, it's an equation like yt is equal to beta plus theta 1 xt minus 1, theta 2 xt minus 2, theta 3 xt minus 3, theta 4 xt minus 4, like this, where yt is the value at our time t. That means at this current point of time where we want to predict. And as I already mentioned, beta is the constant, which is like constant term. And what we are trying to predict is these coefficients for the lagged values. X and all these xt minus 1, xt minus 2, xt minus 3 are the lag values for which we are trying to use to fit this model. And we are trying to predict the coefficients for this lag value in the form of beta 1, beta 2, beta 3, or theta 1, theta 2, theta 3, and all. So this is how this autoregressive model works. And there will be some, we need to add some noise value to this one, which is a random error, which we can't avoid. So we will be adding an random error value as well, and we will be using lags to the number of lags which we mentioned. So if you look at this one, we will be calling autoreg, which is auto regression model from stats models. Stats models is another library where we can find this autoreg and arima and sarima, which can be used to make forecasting solutions. So, and we tell like what is, we give that the data to train, and then we give some data to forecast, and then we try to see how well the particular model is getting trained. Here, if you look at this one, the model is not working effectively. I mean, none of these models are trained, because I have to compromise on the quality, because this while running this one, even though I use this free GPU, the model is getting terminated because of higher RAM consumption. The second one is moving average. Moving average is in case of moving average, what happens is like it will calculate rolling averages. Like for example, if I say take last 24 data points, it will take from data point 1 to data point 24. It will take all the values, and then it will calculate average value and use that value for that particular point of time. And in the next step, it will ignore the first data point, and it will start from 24 to the next data point before the current data point, and then calculate the moving average value and use that value. So it starts calculating the value like this. I mean, it will be like rolling average. It will be calculating rolling average, and the basic idea behind this one is like it will try to smoothen the data. When we calculate moving averages, you can see like this noise, whatever is appearing here, will be smoothened, and the data graph will look like this rather than the fluctuations you are observing here. These fluctuations will go away, and you will be observing a smooth kind of data point in case of moving average. So that's where that's how moving average model works. But what happens is like it will not take into consideration this particular seasonalities and all this, and that's why this will also not be an effective model in to make forecasting. The equation which that will be used in even in this case will be like yt is equal to c plus theta 1 into xt minus 1, and we can't use xt minus 1 here. We have to use error term because we need to calculate average values for that one. Et minus 1 and theta 2 et minus 2 plus theta n up to theta q et minus q, where q will be the order of moving average, where we are using the window here. So we need to use that window value, and we will go up to that range to calculate the error. And it is the random error value within that one, so that the value, what happens is here is like it will smoothen the data points here. So that's how this moving average model works. And the other one is ARIMA model. ARIMA model is a combination of auto regression as well as moving average model, and an integrated part. And there will be an one more component which is integrated into this ARIMA model, which is integrated part. So ARIMA So what happens in case of ARIMA is like ARIMA combines this auto regression and moving average models along with differencing to handle the trends and make the series stationary. As I already mentioned you, one of the assumption in forecasting is the stationarity of data. If the stationarity is not available, then the data will not be that smooth, and we have to the forecasting efficiency will get impacted. So that's why this differencing component is introduced into this one along with AR and A model, which will handle these trends and make this entire data time series stationary. So this ARIMA model is one of the powerful tools for forecasting. The terms AR and I and MA. You can see AR, I, and MA, right? These are the individual components. AR means auto-regressive part, which uses past values to predict future values, just like what we discussed in AR model. And I is integral part, where it will try to find out the differencing the series to remove the trends, and it will make the data stationary. And MA is moving average part, where it will use past forecast errors for prediction. Like it will calculate past error, and it will try to use that error to make the current prediction effective. So that's how this AR and I and MA are used to predict the component. And here there will be three important terms which we need to pass. You can see the order here, right? This is nothing but which are nothing but P, D, and Q. P is order for ER term, and D is degree of differencing, and Q is order of moving average term. So these are the important components, and by adjusting this one, you will be able to build an effective ARIMA model. So these components are most important here. And if you but through this, we are using the stats model to build ARIMA model again, and we are trying to forecast that one here. And even though this model is not that good, and here, if you want to try this ARIMA model, try this. Here, in case of ARIMA model, what happens is it is same like ARIMA model with the difference of seasonality within this one. If you see, we will be using seasonal order as well along with order here, and then we try to make a forecast on top of that one. Only thing we'll be adding here is the seasonality. We are taking the seasonality into consideration while forecasting for this particular data. And another way of predicting or doing forecasting is by using XGBoost or distribution attendance link. So another way of predicting time series is we can use any machine learning algorithm to make predictions on top of this one. But before doing that one, as we have only date and the target variable, we need to create our features. So here what we can do is like in order to create features, we can create lags like lag 1, lag 2, lag 10, lag 20, lag 50, like that. Depending upon our own analysis and depending upon the data, we can create 24-hour lag or 1 day lag or 1 week lag or 1 month lag and use all these features in order to create features and then use this features data to make predictions. This is same like what we did yesterday, like creating the features and then using that features to train the model by dividing into X train and Y train. We are doing the same thing, but only difference is like as we have only time series data, we are creating our own. We are creating our own features from the time series data by using lags. Or what we can do is like we can create seasonal data, or we can create whether weekday or weekend, or we can create day of a day weekday on that particular time period. So we can use that all these features and we can try to predict this one. You can see here this model is fitting effectively for the test data. You can see here, and this is working effectively. You can see in these most of the cases this is not effectively predicting, because for the test data you can see that even for Arima also it's compared just a straight line. It's not taking into the seasonality component here. Slightly, I mean, this entire moving average is completely, I mean, it's like taking average from previous data and then smoothing the data here. And the AR is like same like Arima, and it's completely slow because the values I used for Arima are comparatively wrong, because I used less orders in this case. That's why the model is not working that effectively. Let me see if this works. Let us see what happens with this one. I don't have that attendance link, so Sushmita has to send that one. I don't have that attendance link.
Yeah, so students kindly concentrate on a class. I will share the attendance link, then you can mark the attendance.
I think I need to run this from first. So as of now, you can try this one. Keep changing this. Yeah, Pushpanjali, if you have any question, you raise the hand. Please go ahead and ask. No question, I guess. Yeah, so you need to run this one because I need to define this Arima once again. The terminal got crashed. That's why it forgot whatever we initiated in the initial level. So we can run this one once you get this notebook. It will run. And coming to the XGBoost, you can see like this XGBoost is able to effectively. It is closest to what the actual values are. So that means you can understand that it was able to do it is able to do perform effectively. So there is one thing you can try to do this one. You can create some more features and then train this model to have better performance. And yeah, now this is about AR, MA, and Arima and Sarima. Now we'll be going to profit model, but before going to profit model, we'll try to understand. As I've already mentioned you, it's like entire data analysis. We'll try to understand what happened, what are the different features, and as I told you we created some features, right? So we try to understand what are different features and how the consumption is varying. You can look at this plot where we are trying to segregate data into each weekdays. That means what is the grouping by this consumption on Mondays and Tuesdays and Wednesdays, and the same time segregating for the data into further dividing the data into different seasons like spring, summer, fall, and winter. And you can observe this from this box plot that the season is having impact on consumption. You can look at this one. The summer is having highest consumption, and I mean overall average value as well as highest values are high for this particular summer, whereas the next high is observed for winter, whereas for fall and spring we observed average values in the lowest trend. So from this we can understand like the consumption is comparatively dependent upon summer and winter. I mean, you can even by common sense we can tell this one. But when you deal with real time data, like if you want to assume insolation, it might be more during the winter season, or it depends. Sometimes the data will surprise you. I mean, even in assume that the sales, and when you are dividing the sales into further categories, you will be able to derive better results, or you will be able to understand, get better information from these results. By dividing the plots into different categories, you'll be able to get better insights from this information. That's why here you might tell like, okay, by default we know that in summer there will be energy consumption, there will be peak energy consumption. I agree with that one, but this is for your understanding. Just imagine that if you apply these two sales by segregating them into clusters, in most of the cases that will surprise you, and you will understand, okay, what is happening in this particular series data. And then yeah, this we already did. We try to consider the data mass index, and now these are also not necessary. Yeah, now we'll be starting with profit model. So here, same way, I'm splitting the data from this particular date, and then considering that data as test data beyond 2015, and before 2015 the data is considering for training. So you can observe the data for both training and testing, and you can see how the data is fluctuating. We already saw the data, so now let's go to a profit model and try to see how this particular profit model is working, and try to interpret the results from this particular profit model. Okay, so if you look at this model, we are initiating this profit model by calling it from from profit, and by calling this class, you can see what are all the values it takes. By changing these particular values which you observe, like what is the growth, and what is the change points, what is the number of change points, what is the daily seasonality, do you want to increase holidays, do you want to include holidays or not, what is the seasonality mode. There are a lot of hyperparameters which you can adjust in order to increase, or in order to enhance the performance of your particular profit model. Right now, I'm using the default parameters here, and we are using our train data, and then we are fitting the model on top of profit model, and then we are using our test data and trying to see what this particular profit model generates. Like for example, if you look at the data initially, we have only time information, and the consumption information. We don't have anything else from the data. And now, once you look at, once you pass that, once you try to predict that for the test range, what happens is like it will create multiple columns within this data frame. You can see that this is the test data frame that is being created by using profit algorithm that was trained by our training data. That means we are just predicting for this trend. And here there will be multiple columns like trend, y hat lower, y hat upper, trend lower, trend upper, additive terms, and weekly lower, year and yearly lower, and multiplicative terms, and finally, what is the y hat value? Y hat is nothing but predicted y value. That means predicted consumption value. I will explain these terms through a graph here. So if you plot that forecasted data for y hat is nothing but the final consumption value. This is the final value which you are trying to predict. This is the y hat. So you can see that this blue color value is the data that is generated by profit model, and you have seen these terms, right? Y hat upper and y hat lower, and trend lower and trend upper. This profit model, instead of just predicting the value, what it gives is it gives a range of prediction. Like instead of telling like the sales will be around 10 crores for this next month, it will tell like along with making the 10 crores prediction, it will also give a range of variation. Like it will tell like the predicted range for sales for next month will be from 12 crores, 8 crores to 12 crores, and it will give the range along with the predicted value. Along with that one, it will also give the trend range how the trend is also moving. You can see the trend upper and trend lower also, right? It will give how the trend values is going and what will be the trend. I mean, here it's not visible for you because the plot is kind of clumsy here. So it will also give you the trend range and it will show you the trend range so that you will understand how the trend is moving and what will be the minimum value within the trend and what will be the maximum value within the trend. So that's how forecast values gives, and it also gives you what will be the weekly values and weekly lower values, weekly upper values, and what will be the additive terms and what will be the multiplicative terms within this one. And you can see here. The trend, as I told you, when we there is one more method in profit model where you can divide all these prediction into different components as like trend component, seasonality component, weekly component, yearly component, and daily component like that, and even hourly component. So we can divide this patterns into different components to understand what is happening with our data. Like for example, you can see the trend, and as soon as the data, if you look at this trend data, we can observe one thing that the model is more confident when it is predicting for the data that is close to the data till it is trained, and as we move the data to further, it is the confidence level of the model is slightly decreasing, and that's why it is increasing the trend range. That's why we observe a wide range for last data points. That's why there will be huge margin of error. That's why, so what happens is like as we keep on predicting, there will be a lot of uncertainty related to the data as we go on into further future. That's why there will be a wide range for this trend. And when you look at the weekly patterns of consumption, we observe that on Sundays and Mondays the consumption is comparatively low, and on Tuesdays, Wednesdays, Thursdays, and Fridays the consumption pattern is comparatively high, and it started decreasing from Saturday. That means this trend is observed in the entire data and the predicted future data as well. So this is one of the important components. We can understand how our predictions are working with respect to weekly division. And similarly, we can also look at yearly data. That means for every month how this is operating, and we can see like during the February months there will be peak, the consumption is peaking, and then the consumption is dropping as it goes down to till May, and again from May it's peaking up, and then from May it's peaking down to November. So this kind of trend is observed in for every year in the entire data. That's why that is what this plot conveys, and these are one of the important information that can be understood by profit components, and we can further divide this into daily or quarterly also, so that we can have better information related to the particular predictions. And now here this plot shows us how our predictions are working. If you look at this one, this blue color represent the predicted values, whereas the red dots represent actual values. You can see that the values are very close to what actual values are. The model predicted effectively with what actual values are. That means the profit model is working effectively in this case. When we want, if you want to understand, segregate this one and look how this is working, this plot is like we are dividing this for a month. So you can see here we are plotting this for just a month after 2015 for the test data to see how well it is fitting the data. You can see that most of the data points are falling within the range of y hat upper and y hat lower, and very few data points are going beyond that y hat upper or y hat lower. That means the model is performing well and better, and so we can safely say that the forecasting values are very good. And this is for weekly data to understand. I mean, we are further compressing the information to see how well the data points are, and you can see that for the entire week, apart from one or two data points, the data is working effectively here as well. And these are the metrics like mean squared error or absolute error, mean absolute error, which we are mean absolute percentage error, where the model is making. So the mean absolute percentage error that the model is making is around 8.1%, which is comparatively low. So we can consider this model for predicting, for forecasting any kind of series data. And there is one other important thing which can be done in Profit, like I already showed you, right? when you see there will be a component where we can take into consideration the holidays. Here we will be doing that one. In order to do that one, what we are doing is like we are creating a calendar data frame and passing that data frame to the Prophet model to understand the holidays as well. So here we are passing this holidays data frame along with data. So what happens is like this will consider the holidays and try to include the impact of holidays in the data. Like for example, when you take sales data, the sales of majority of goods will be higher during the holiday season. Like in India, it will peak during Dasra festival or Diwali festivals or Pongal festivals and or during Christmas and sometimes even in nowadays during these big billion sales or Prime Day sales, something like that. There will be peak. The sales will peak. So while doing forecasting for sales, we can use this holiday component as well, so that that component or that impact that will these holidays will have on the predicted value will be considered while training the model. So the Prophet can provides an option to do this one. So we can pass this holidays data frame to this one. Here, what we are doing is we are taking US federal holiday calendar and using that holidays as data frame to pass to the Prophet model. We are taking this US holidays because the data set is belongs to US data, and that's why we are taking this one. And when we run this one, we can observe the similar trend here, and we can see in holidays during some of the holidays, you can see the peak consumption, this peak values during the holiday consumptions, and then it will try to include this factor as well within the model to make forecasting decisions. So that's how we can include this particular holiday season as well. If you want to include seasonality also, then it allow you to include the seasonality pattern as well, so that the model will consider that information also. So here we are taking July 4th predictions because July 4th is an holiday in US, and we are trying to see how well it is fitting with the information. And you can see that the data points are close to what within the range of y hat upper and y hat lower, making the forecasting model more effective. And in order to make a prediction into future, that means so far we used prediction till our test data only, and if you want to predict beyond that one, we can also predict beyond that one and pass this information. One important thing while using Prophet is Prophet always needs data within like in this format only. It should have a DS column and y hat column. DS column will be your date column, and y hat column will be the parameter which you want to predict, and the names also for the column should be like this only. So remember this one. If you want to use Prophet, you need to have data like this, and it should be like this, and it should not be any other column as well. So any questions so far that's related to forecasting? Any questions, anyone so far? I will take 5 minutes break. I will have some water and come. I will be back. Give me 2 to 3 minutes. I will be back in 2 to 3 minutes. Then we'll go with clustering algorithm. I will be back in 3 minutes. Yeah, so let's start with this forecasting, clustering algorithm now. Let me share my screen. And another important thing you need to remember is just like forecasting, even this clustering algorithm will also requires lot of data analysis. So we need to understand how well the data is. How I mean, are we able to derive any of the clusters by looking visually looking at the data or not? So most of these clustering algorithms will, I mean, clusters will also work in a similar way. And now in this case what we are doing is like we are trying to segment customers, and this customer segment is mostly used in different say to classify customers for certain products, or some for some advertisements, or for some from some viewership, or for some category of products. So they, I mean, in some of the cases, are in, you can say, half of the time, what happens is like instead of directly using clusters as the final output, in some of the cases, what we do is we use these clusters as features to train models also. So there are a few cases where we use these clusters to train the models to make predictions effectively. Because this cluster information is also used as one of the feature to train the model, which will enhance the performance of our model. So that is one thing, one other important thing which is related to clusters, and the clusters are obviously used as a final algorithm, final output as well. And this clustering algorithm generally work based upon distance metrics. And so we try to find out data points. We try to create clusters based upon the data points where the distance between data points within the cluster is minimum, and the distance between data points between two different clusters is the maximum. So that's our main goal, and we try to create clusters in similar way. So here in the initial step we are loading the libraries, and then we are using this sales data from sales data to create, to do this particular clustering algorithm. And first we will be doing, I mean, this is from, again, this is from Kaggle data. This is like sample sales data, and we are using this sales data to segment the customers across different clusters. And to understand the data, we have order number and quantity of our quantity of ordered product, and what is the price of each product, and what is the order line number, what is the product sales, and what is the order date, and what is the status, quarter id, month id, year id, address line, city and the state, postal code, country, territory, contact persons, first name and last name, and the deal size. Deal size like me, small size or medium size or maximum size. There, I think we have around 25 columns. So we have around 25 features. Let's see how many, what are the features. So these are the features that are, I mean, these are the columns that are available in the data set. I mean, some are not visible. That's why I use this one. So we have customer name, phone number, address line, address, city, state, postal code, country, territory, contact last name, contact first name. If you look at this data, by looking at this data, you can understand like we have customer name and again we have contact last name and contact first name. So which is not required in this case. Similarly, when you have postal code, I don't think you need any information related to state or city because postal code will be more than enough for us to create a cluster. Because I mean that will by default derive the information from within these two, so we can drop that one. And so like that, you need to, I mean, you need to do analysis on your own, and you need to try to understand what are the most important features, and then what are the features that are that can be used in order to train our algorithm. And here there is some glossary about what is what does that particular column and what is the information that particular column provides you. So status shows like whether the status, whether the product was order was shipped or not. And the quarter ID is nothing but quarter of the year. Like for example, if we take a year, Jan, Feb, and March will be considered as first quarter, and April, May, June will be considered as second quarter, May, and next the third quarter and fourth quarter. So this is considered as quarter ID here. And MSRP is like MRP only, but manufacturer suggested retail price used in USA. And the deal size is like how many products were brought, and size is segmented into small, medium, and large scale, I guess. Let me see how this particular what are the value counts of the particular size is. So we have three scales: medium, small, and large scale. And most of the deals are falling within medium and small scale, and very few deals are in large size. So let's understand data summary. For it's like information about data which we have seen in our last two projects, classification regression as well. So we are trying to look at what is the total number, are there any nulls, total number of null counts, and is every data column representing the data effectively. And so you can see like order number is integer, okay, that's fine, and the price is float, that is also fine. And what is the object? Product line object, obviously. Order date should be in date format because date cannot be an object, and the status can be an object because whether the product is shipped or not, we need to. It will be an categorical data, so obviously it will be an object data. And product line, what is product line here? It's not showing here. Let's see what is the product line. Okay. So we have what does that particular product belongs to, line belongs to. So then it will be an object data type. So we can understand that it's object and it's representing correctly MSRP. It should be integer. I guess it should be in float value. Yeah, that's fine. Product code will be an object value. Customer name object value. Phone number should be, but they will be country code. So that's why it can be an object. And address line. These are all so by looking at this one, we can understand the data frame is being represented effectively. So we don't need to make many changes except to change that data date. And we are not going to use date in this case until unless it's time. This is not time series data. So if it's time series data, obviously we need to convert that into datetime format. As this is not going to be time series data, we are not focusing that much on converting that one. So now we try to understand how each feature is being distributed across the data values. So you can order number is an unique order number, so we don't need to understand this particular case because it will be a unique number that will be assigned to that particular order. And the quantity order distribution looks like most of the data falls within the range of 20 to 50. So the entire data or 90% of data falls within the region, which will give us like this is more important feature here. And price of each, I mean, every single price of each single product distribution tells us that there are a huge number of data points for a price of 100. So that means most of the data is focused at this point, and very few data points are focused in this less than 100 value. And order line number, we don't need this order line number because it is also a unique number. And we can look at the sales values, and we can look at most of the sales values are falling within the range of 1500 to 8000. Similarly, quarter ID, yeah, you can see majority of sales are happening in the final quarter of the year. That's one important information we can derive from this plot. And month ID, and most of the sales are happening in November. You can see, you can look at maximum sales are happening in November. So this information will help you in allocating your resources. Like for example, if you give this information to consumer, what he can do is like he can try to allocate resources based upon this information. What he does is like he will try to focus majority of resources during this period and try to maintain maximum inventory during this period and during this November month, and least inventory during the sixth month, means June. So that what happens is like he will be maintaining optimal inventory or optimal, he will be having optimal resource like employees or any other equipment that is required to do the sales. So he will be able to optimize the resources and optimize the inventory that is maintained by the store. So and during the quarter also he can do the same thing. Year I guess don't need because there's certain year there's more. I don't think this will be of importance here. And if you look at this one, majority of sales is being derived from the product with a maximum price of around 175, up to 175, and peaking at 100, which we already observed in that case. And he already mentioned some doesn't make any sense like order line number because it's an unique ID, and we can't take any advantage of this one. And quantity ordered also will not give that any information to us because it doesn't give maximum information. And there are long tails if you observe for price each, so which will make us which need to be addressed in the later steps. I already have written all the analysis here, and we can go through this one to understand this data. And now to understand, to describe the data set or to get statistical information about all the numerical columns, we are using this describe method here. You can see the mean values for each individual features. And from, I mean, order number doesn't make any sense because order number is an unique value. And so you can see the mean value of quantity ordered is 35. That means in general the total number average values of ordered is 35, and standard deviation is very less. That means the variability of orders is quantity orders comparatively low. And when we look at this price of each piece, the mean value, average value of each good that is ordered is 83 USD with a standard deviation of 20, which is comparatively high. And this order line number doesn't make any sense. And if we look at the sales, even though the mean value is $3,553, the standard deviation is very high here. You can see like 1841 is the standard deviation, which indicates high variability within this particular feature. And yeah, and this attribute price each, you can see that the mean value is close to the maximum value, because which we already observed from the plot as well, which indicates that there is a long tail towards the left side. And that means the frequency of occurrence of higher value beyond 80 is more when compared with lower value below 80. That means the higher value goods are being sold more in this particular data set here. And for MSRP, the minimum mean value is 100 and maximum value is 214, and standard deviation is 33, which is, sorry, standard deviation is 40, which is quite normal. And now what we are doing is like we are creating a copy of this data set to do further analysis here. And we are dropping all the unnecessary columns like order date, product code, customer name, phone name, first name, and all these things. And then we are creating these plots where we are creating this bar plots here, where we are trying to see the number of occurrence of each value count within that particular feature. And you can see this information here. Most of if you look at this state column here, most of the sales are being coming from California state, and next sales are coming from MA. And if you look at the country, majority of sales are happening from USA, and the next most sales are happening from Spain and France. If you look at the territory, majority of sales are happening from EMEA territory. And if you look at the deal size, majority of sales are happening in small and medium scale, and very less sales are happening in deal size. And I'm explaining this to you because this is how you analyze. And in majority of cases, if you are working with companies which like Walmart or Pepsi or Coca-Cola or any retail based business companies, your focus will be more on these clustering algorithms, and you need to you have to give all this analysis along with your model, because the major focus will be on your reports based on this analysis. You need to provide analysis based upon the data, based upon the visualizations, or based upon the analysis you do from the data, and provide that create a report based upon your analysis, and then you have to provide that report to the end user, who will use this report and then make business decisions. That's why the major focus when it comes to forecasting, or it comes to clustering, or anomaly detection. I mean, anomaly detection will have impact. I mean, will be crucial in model prediction as well. But when it comes to clustering and forecast analysis, you need to do a lot of analysis apart from building the algorithm. So that's why I'm trying to explain you what happens in this business scenario questions. So you can we initially, if you look at this problem statement, we have some of the questions here. You can answer all these questions from looking at all these plots which we created through our visualization tools. And you can also use Plotly, which will be like which will kind of help you in creating 3D plots. So use that one, try that one. I will in the next session or somewhere I will try to give you the Plotly code as well, and I will try to explain how to deal with that Plotly library also. So to understand this one, to understand what is the change in sales over time, we are doing this forecasting solution here. We are trying to understand if there is any change in sales, or if we can observe any trend within the sales. As you can see, we don't see any trend within the red one, but there are a lot of outliers, or the peak sales that is happening at a certain period, certain time period. So we can use that information to answer certain questions like what is the peak period of sales that is happening, which we can also get that information by in previous plots as well. So now here we are trying to create the same plot for each labels, like we are dividing the labels into different by create I mean for month, and grouping by the month ID, and the product line by state, by country, by territory, and deal size. And we are creating these plots which will help us in understanding what is happening with our sales data, or what is happening within our, I mean, this like kind of repetition, but this gives more insights from when compared with our previous data, because here we are grouping by product line, or we are grouping by month ID, we are grouping by state, and trying to see what is happening with respect to sales. There we are predicting number of occurrences, whereas here we are trying to predict the sales here. So that means the previous plots were the number of occurrences of that particular event, and which will give you like what are the number of orders that have happened for that particular region, or for that particular state, or for that particular month, or for that particular quarter. Whereas here, what we are doing is we are trying to predict what is the total quantum of sales that is happening when we divide across month. Like say the similar thing which we observed, like in November there are a huge number of sales, as was observed that number of counts in November. And in product line, classic cars was the major revenue generator for the store. And as we observed, number of orders for more for CA, and here also the total quantum of sales is also more for CA. Sometimes there is a possibility that what happens is like even though the number of orders from CA are more, probably NY or MA might generate more revenue because NY and MA might be ordering highest cost products, whereas CA is ordering low cost products. So you can also observe these kind of trends within the data, and you can understand these three plots also when compared with the previous plots. And then I will be giving this notebook to you. So you can go through this and understand what is happening with this one. And I don't think this will, as this is B2B customer data set, this might probably give you some insights like who is generating more revenue, so that you can come up with, you can tell your marketing department to give some freebies to that particular distributor. Like for example, you can see this particular green one. Who is that? Maybe this Sominam Sonis. So you can probably offer him some freebies or gifts to him for maintaining the highest sales. So that what happens is like as we are giving some freebies, he will be automatically be interested more in generating more revenue, and we can also convert these particular customers to increase their sales because they are already doing good, and we can probably offer some freebies or gifts to increase the sales. That will have more impact, that will increase the revenue of that particular business. Whereas if you look at this one, this particular person, La Rosalie gives, who is ordering very less quantity from, who is generating less sales, what we can do is like we can have a discussion with him and try to what is the is there any issue in selling the products, or is there any feedback from the customers because of which the sales are low in that particular region, or is there any factor which is impacting our particular sales. So this is how we give insights to them, to the marketing team, our sales team, so that they can make decision on top of that one by maximizing the revenue by utilizing minimum resources. So that's how we can generate insight from this one. And apart from this, and we are trying to find out correlations here. I think this is self-explanatory. I will directly um, go to the model. And here's the, it's nothing but heat correlation map. Yesterday I showed you heat correlation map, right? The same thing by default. Obviously, number of sales will be correlated with the price each, and year ID is correlated with this order number because we in general order numbers are will have an year ID as subcomponent within that one. So that's why you find more correlation here. And the quarter ID is also having correlation with month ID because we know that quarter ID is, I mean, month is part of quarter ID. So obviously there will be highest correlation. That's how you, I mean, you try to understand if there is any correlated parameters, so that multi-correlation will have impact on training the model. So now here we are creating the data set by dropping unnecessary features, and then we drop the features that are not important, and then trying to create, try to see if they try to create clusters by using the algorithm. So here I'm using some pipeline from sklearn, and we are using imputer because there are some null values within the data. And the pipeline, how, I mean, I will explain you the how this pipeline works. sklearn will provide you a pipeline where you can define how the data should pass. Like for example, in this pipeline, I'm creating three steps. When the data passes through the pipeline, first thing will be imputer, and to the imputation, I'm using simple imputer strategy, and my strategy is medium. And the next technique that next transformation that will be applied will be transformation. For this one, I'm using EO Johnson transformation that will be applied on top of the data. And then after passing through this one, then the data will be standardized by using by doing the scaling by applying a scaling transformation on top of the data, which will use a standard scaling technique. And finally, after passing through all these steps, it will give the final pipeline, so sorry, final data with me. That means instead of manually doing this one, what we can do is we can create a pipeline with the strategy, like for example, you want to do if you want to add one more step like normalizing, you already added, and if you want to add one more step like dropping the rows or feature selection, you can add one more step here, so that the data will also pass through that particular step, and then final data will be the data after applying all these transformations. Once we have the transformed data, we are creating an column transformer in order to create encode the data, where we are using one-hot encoding to apply on top of categorical data, which will be converted into numeric, so that the model will be able to understand that one. So here we are passing through the second pipeline, for which we are using column transformer, and we have the data prepared, and we are converting that into an array, and then we are using k-means algorithm in order to create the clusters. But there is an concept called we don't know how many clusters we need to create, right? So far we didn't decide upon what is the number of clusters that has to be that has to happen. In order to decide what is the ideal number of clusters that we need to create, there is a concept called elbow graph, where we start from creating one cluster, second cluster, third cluster, fourth cluster, fifth cluster, like that. We create n number of clusters and try to see what is the WCSS value, which is nothing but distance value. And wherever there is a sharp bend like this, it's nothing but, if you look at this plot here, it looks like an elbow here. Wherever you see an sharp bend, either like this or like this or like this, you can understand, like, okay, from here there won't be much information that I will be gaining from this. So I will use this number of clusters as optimal number of clusters, and use my k-means algorithm to create that many clusters from my data. Just a second, I will back. Yeah, so once we decide the optimal number of clusters here, again we use k-means algorithm to decide to assign an cluster for each data point. So this is what we are doing here. And then if you look at this one, sorry, this is for plots. Yeah, here you can look at the clusters. So we are creating 4 clusters here, because as we observe from that one, what is the ideal number of customers which we clusters which we decided. Yeah, we are using 3 as our clusters. We can change this number to 4. I think 4 will be an better indicator here. So we'll use this as 4 clusters. So now we can see 4 clusters here. So that means it will algorithm will allocate one cluster name for cluster number for each cluster, and then we can see that these clusters, how these clusters are divided across this entire data set. So that's how this clustering algorithm works. Apart from k-means algorithm, there are other ways in dealing with this kind of this clustering. Any questions so far? Anyone? Any questions? Are you clear with how this clustering algorithm is working? Anyone has any questions? So this clustering is an unsupervised learning method, where we don't have any target variable. If you look at the data, we don't have any target variable which we are going to use, or we are not going to pass any target variable. We don't have any cluster number. What happens is, like, we are creating that target that cluster number here, and in case of clustering, we don't have any target variable which we are trying to predict. What we are trying to do here is, we are trying to group all these clusters, I mean, all these data points into individual clusters, so that we can have an idea about how these particular how these data points are interrelated to each other, so that they can be combined into a group. Apart from k-means clustering algorithm, there are different other algorithms as well in order to do this clustering. Where one other algorithm is hierarchical clustering, where it builds an hierarchy of clusters by either merging or splitting the data. Like, I mean, it will start with one point and either it will start combining or it will start dividing to try and see whether this cluster, this separation works effectively or not. So this is how this hierarchical clustering works. And there is another and more prominent clustering algorithm which is called as DB-scan. Our full form of DB-scan is density-based spatial clustering. Something after that, I don't remember the full name. So it's considered as DB-scan, and where it will create data point. It will group data points based on density and separating dense clusters from sparse clusters, and it will use that information. I will view that plot. Let me see how DB-scan works. It will give an idea to you. DB-scan diagram. Let me show you this. So if you look at this screen, you can see there will be there are different concepts in relation to DB scan. That is, our main goal will be to find out core point, border point, and noise point. And see, we want the core point, which will be the main point in that particular cluster and should not fall within any of the cluster. And the border point should be the point which should be the end of that particular cluster, and the noise point will be something, even though belongs to this cluster, it will be away and which we cannot use effectively. So it tries to optimize this algorithm and tries to optimize the distance between these core point, border point, and noise points, and then try to segregate all these data points into different clusters. So what we do in case of DB scan is that first we will define a neighborhood size and minimum number of points within that are expected within that particular neighborhood, and then we start with identifying the core points, which should have sufficient enough neighbors. If there are no neighbors, then that cannot be considered as an core point, and then expand the cluster from core points by including directly and indirectly the connected points. Whatever the points that are directly or indirectly connected will be considered, and then the cluster will be expanded up to that level. And because of this, what happens is like these border points which are linked to this one will be in the border range of that particular cluster, and then any point beyond that level will be considered as a noise point and will not be considered within that particular cluster. And the reason for success of this particular DB scan is it handles noise effectively, and even it will be able to identify clusters of different types of shape. Like for example, if you have an two clusters where one cluster is having U shape and the other cluster is having a circle within that U shape, still the DB scan will be able to identify that clusters. And this is one of the major algorithm that is widely used in industry. And there are other methods as well, like mean shift clustering and Gaussian uh, Gaussian mixture models or something is there, and spectral clustering is there, and agglomerative hierarchical clustering is there. There is some optics also. So there are other techniques as well. It depends upon the problem you are working and your scenario. This is about clustering, and this is related to the coding for clustering. So anyone have any questions so far? If you don't have questions, then we can drop. I will wait for 2 minutes, or 1 minute. And if you don't have any question, then we can drop the session. Sushmita, let's wait for 1 minute. And if no one raises hand or no one sends a question, I will drop.
Yeah, sure, no problem.
I think no one has any questions. Shall I drop, Sushmita?
Yeah, yes, sir. If you're done for the
Yeah.
day, we
Thank you,
can.
everyone. Thank you for attending the session, and have a nice day.
Yeah, thank you, sir. We'll meet again by tomorrow at 7:30. Yeah, thank you. So, students, I'm sharing attendance link again on the chat. Kindly mark your attendance. I hope you everyone marked an attendance. So, I will wait for 1 or 2 minutes, then we'll wind up the session. So, thank you all. Kindly join the session by tomorrow at 7 p.m. I mean, sorry, 7:30. Thank you, everybody. Good night.